So hello and welcome to the continuation of AP Chemistry 3 of 3 online. Today we're going to go on to the next chapter, chapter 16, which deals with solubility equilibria. As we've already talked about some equilibria, the nice thing about working with solubility equilibria is since one of the components is a solid, its concentration is always 1. And so we only have to worry about the ions that end up in solution from dissolving that solid. And this is one of the tricks to working with any kind of solubility problem. You always want to look at it from the standpoint of the solid dissolving in solution rather than the solutions precipitating to form the solid. It makes the math in general much easier, and it's usually easier to follow what's going on. So let's consider a nice simple precipitation reaction. So let's consider a simple precipitation question. Consider an aqueous solution that we made 0.1 molar lead nitrate and 0.2 molar potassium sulfate to start with. What's going to happen? Well, the Ksp for lead sulfate, 1.3 times 10 to the minus 8, suggests that, we're probably going to get a precipitate. If we multiply the concentration of lead ions, 0.1, times the concentration of sulfate ions, 0.2, we get 0.02, which of course is a lot larger than 1.3 times 10 to the minus 8, which indicates, yes, we absolutely are going to get a precipitation out of this. The nitrates and the potassium ions are, of course, spectators, and we're not going to worry about them. So what do we do now? Well, like we said, the first step is we assume 100% precipitation by the lead and the sulfate ions. That means we're going to end up with lead sulfate, and the solution is still going to be 0.10 molar sulfate ions. We now have the new equilibrium. Lead sulfate dissolving to form lead ions and sulfate ions in solution. So the lead sulfate would start to dissolve. The Ksp for lead sulfate, 1.3 times 10 to the minus 8. The original concentration of lead sulfate this time is now 1. There wouldn't be any lead ions in solution. We've assumed 100% precipitation. And the remaining sulfate in solution is 0.1 molar. Have to solve for x. X times 0.10 plus x equals 1.3 times 10 to the minus 8. We're expecting x to be small, so 1.0 plus x is simply going to be 1.0, and we find out that x is 1.3 times 10 to the minus 7th molar lead ions. The sulfate, 0.10 plus 0.13 times 10 to the minus 7th, of course, is just 0.10. Now let's consider a more complicated situation. Suppose we make a solution that is 0.1 molar silver nitrate, 0.2 molar sodium chloride, and 0.15 molar potassium chromate. What's going to happen? Well, the Ksp for silver chloride, 1.6 times 10 to the minus 10th, and the Ksp for silver chromate, 9.0 times 10 to the minus 13th, certainly indicates we're going to get precipitate out of these solutions. But the question is, what precipitate are we going to get? Are we going to get silver chloride? Are we going to get potassium chromate? Or are we going to get some combination of both of them? And so we'll assume to begin with that both the ions, the chloride and the chromate, will cause 100% precipitation of the silver ions out of solution. Therefore, the 0.1 molar silver ions and the 0.2 molar chloride ions will give us silver chloride, leaving a solution that would be 1.10 molar chloride. We'll assume that 0.1 molar silver ions plus 0.15 molar chromate ions would give us silver chromate, and again leave a solution that's 0.10 molar chromate ions. So what would the concentration of silver ions be in the resulting solution at equilibrium? Well, first we have to solve it for silver chloride. The Ksp for silver chloride, 1.6 times 10 to the minus 10th. We have silver chloride. We are assuming we don't have any silver ions remaining in solution, and the chloride's 0.1 molar. So some of the silver chloride dissolves to give us some silver ions. X times 0.10 plus X equals 1.6 times 10 to the minus 10th. X is going to be 1.6 times 10 to the minus 9th. Since 0.10 plus X is going to basically be just 0.10. And so if there was nothing else other than silver and chloride in the solution, the concentration of silver ions would be 1.6 times 10 to the minus 9th. Now we have to consider the reaction from the standpoint of the silver chromate. Assuming 100% precipitation by the silver chromate, concentration of silver chromate's 1, there aren't any silver ions in solution again, and we have 0.1 molar chromate ions in solution. Again, we solve for X, and in this case, X turns out to be 3.0 times 10 to the minus 6 silver ions. And so we have our solution. And sitting on the bottom, we have silver chloride and silver chromate. The silver chloride is sitting there dissolving 1.6 times 10 to the minus 9th molar silver ions and chloride ions in solution. The chromate's dissolving 3.6 times 10 to the minus 6 silver ions in solution. And so what do we got? Well, we have an equilibrium problem here. The silver chromate is trying to keep 3.0 times 10 to the minus 6 moles of silver ions in solution. But the chlorides are only allowing 1.6 times 10 to the minus 9th chlorides and silver ions in solution. So what's going to happen? Well, what's going to happen is the silver chromate's going to keep dissolving silver ions in solution, and the chlorides are going to keep precipitating them. So are we going to get a mixture of products? No. The result is we're going to get nothing but silver chloride sitting on the bottom. Chromium is all going to be in solution. And this is an important point to note. The Ksp for the silver chromate is smaller than the Ksp for silver chloride. But you have to take into account the stoichiometry. The concentration of the silver ion for the silver chromate is being squared. That exaggerates how much a small concentration contributes to the Ksp. And this is something you have to keep in mind. You can't just compare Ksp numbers by themselves to figure out which compound is more soluble in solution. Where you have stoichiometry, like the silver chromate, then the exponents start playing a big role, and it can deceive you as to who is more soluble of the two. Anytime that you are dealing with a Ksp problem, it is important to keep in mind that the Ksp numbers by themselves don't tell you necessarily what's going on. You have to be a little bit careful about the numbers since the exponents become of great importance. We're now going to consider something else that is very specific to solubility problems. Now we're going to consider something else you have to keep in mind when talking about precipitation solubility problems. Suppose we have a solution, 0.1 molar silver nitrate and 0.1 molar potassium phosphate. What's going to happen? Well, the Ksp for silver phosphate, 1.8 times 10 to the minus 8, is again clearly indicates we should expect to get a precipitate. 0.1 molar silver ions cubed times 0.1 molar phosphate is 1.0 times 10 to the minus 4th, which of course is way larger than 1.8 times 10 to the minus 8th. We'd absolutely expect to get a precipitate out of this solution. And we could go ahead and do it as a solubility problem to figure out how much silver ions were in solution. You might expect that it'd be the same sort of problem if instead of silver nitrate and potassium phosphate, we had silver nitrate and hydrogen phosphate. Are we going to get a precipitation from these two solutions? Well, again, the Ksp for silver phosphate, 1.8 times 10 to the minus 18th. The silver ions, 0.1 molar. And the phosphate ions, well, that's a problem. Because, of course, hydrogen phosphate is phosphoric acid. And phosphoric acid is a weak acid. It has a Ka. And so what is the Ka for phosphoric acid? The Ka for phosphoric acid is 7.5 times 10 to the minus third. But of course that's only for the first proton. Dihydrogen phosphate is also an acid. It has a Ka of 6.2 times 10 to the minus 8th. And even monohydrogen phosphate is in fact an acid, and its Ka 4.8 times 10 to the minus 13th. And so what does that mean? Well, without going through a whole lot of calculations, the fact is that in our 0.1 molar phosphoric acid, the concentration of phosphoric acid is going to actually be about 0.07 molar. The dihydrogen phosphate going to have a concentration of 0.03 molar. That means the dihydrogen phosphate is going to have little success getting rid of its proton, and the actual concentration of hydrogen phosphate in solution is going to be out like 10 to the minus 12th molar. And of those, they're going to have to ionize their protons with a Ka of 10 to the minus 13th, which means basically there is no phosphate ions themselves wandering around in the solution of 0.1 molar hydrogen phosphate, that is phosphoric acid. And this is something to keep in mind. The equilibrium doesn't care about the phosphoric acid, the dihydrogen phosphate, or even the monohydrogen phosphate. The equilibrium is only concerned with the actual phosphate ions present in solution. And like we said, in the 0.1 molar phosphoric acid, there basically isn't any phosphate actually in solution. So in this case, there would be no precipitate formed, even though in theory there's a lot of phosphates. In reality, there are almost no phosphates. And this is a characteristic we see of acids, which is why, again, we separate them from the ionic compounds. The ionic compounds automatically ionize to ions, but the acids don't. They're only partially ionized. And so you have to work out the concentration of the actual ions in solution anytime you have a chance for acid-base equilibrium as part of your solubility equilibrium. So now we're going to have to address the problem of how acid-base chemistry becomes important in our solubility reactions. And that's where we're going to take it up in the next lecture. Have a good day.